Chapter 14 in systems class is all about reactors. Okay, that's a vessel in which a controlled reaction takes place. Very beginning of the chapter lists the 5 main types of reactors: stirred tank, fixed bed, fluidized bed, tubular, and furnaces. There's other types, but they're usually made up of a combination of those 5 main ones. These are the reaction variables. So a reactor is something that's going to have a chemical change. So down to the molecular level, something is changing. You're breaking molecules apart or making in chemical bonds, putting them together. Okay, so this is happening on a molecular and atomic level. And so it's not a physical reaction. This is a chemical reaction. Physical reaction would be something like ice melting into water, water boiling into steam. That's not what we're talking about here. We're talking about actual chemical compositions changing. Okay, they go in as reactants. Okay, that's the raw materials, and then they end up as the products. Okay, one of the reactors that we're going to look at in the hands-on labs is going to be a fermenter. A fermenter is a type of reactor. We put in a raw material of sugar, and then we get the final product. The reactant is sugar is a raw material, and the final product, the end results, is going to be ethanol, okay, or alcohol. And so that's what's happening there. So what makes this change? What do we have to be able to either enhance or decrease the reaction quality? And what we have here is the list of reaction variables. Temperature is a very important reaction variable. Every 10 degrees Celsius that we go up, we increase the reaction rate by 2 times, which means that's going to happen twice as fast. Okay, and that's 10 degrees C. Now that's not true for every single reaction, but that is a pretty good general rule of thumb. That as we increase the temperature, we're going to increase the speed in which the reaction happens, which is going to decrease the amount of time. And that's important for throughput because as materials sitting in a reactor not reacting, we're not making any money off of it. So we want it to react as fast as we can, with balancing with safety. Another thing is pressure. Pressure is not generalized as easily as the effective temperature. Pressure can increase the reaction rate or it can decrease the reaction rate. And the ethanol reactor that we're going to look at, pressure will decrease the reaction rate because what we have in there is a bioreaction, which means it's actually a living, breathing thing. And the fact that yeast is what's doing our reaction. And if it's under pressure, it can't move around as freely. It can't do its job as well. And so that will actually slow down the reaction rate. Other reactors, such as reactors at the refinery, pressure will force those molecules together. It'll jam them into each other. And so it'll increase the reaction rate. So that really depends on the actual reactor that we have going on. Time, so the time and material spent in the reactor, the more time, the more complete. So if we leave our raw materials in there for, let's say, the ethanol reactor that we're going to be looking at for 72 hours, we'll have, upwards of 95, 96% of that reaction complete in 72 hours. Now, if we let it go a little bit longer, like say 96, we're only going to get a few more percentage. It's only going to go up to like 97 or 98%. And so we call that balancing the economy with results. Because that stuff's sitting in that tank, we're not making any money just sitting in the tank. So we want to pump it out, once we get it as complete as possible. Typically with agitation, it's more complete. So we agitate it. That's going to be mixing it up, stirring it. That's going to make those molecules come into contact with each other more often, and so we get a more complete reaction. The concentration of the reactants. So the more pure our reactants are going in, so the more pure our materials or raw materials are going in, then we're going to have a more complete reaction. Okay. Catalyst. Catalyst is something that increases the reaction rate but does not become part of the product. Okay, so it does not become part of the final product. Yeast is an example of a catalyst in our ethanol. It increases that reaction rate. It increases it so much that it wouldn't happen without it. But the yeast does not become, the yeast itself does not turn into alcohol, so it does not become part of the product. Okay. We talk about a lot of other catalysts when we meet in the hands-on lab. We'll show you what some of them look like as well. And then the opposite of that is an inhibitor. Inhibitors hinder the reaction, possibly downstream. And we'll talk about why we add inhibitors later on in the chapter when we get into the safety aspects, but a lot of times the inhibitors come in with the feedstock. So inhibitors might be, back to our ethanol lab that we're going to look at, inhibitors are going to be like bacteria, contaminants, mold, things that might come in our raw material. So if our raw material is not clean enough, it'll have an inhibitor, and that'll hinder the reaction. Two main types of reaction we can break it off to is exothermic. That means it's going to give off heat. Okay, so exothermic reactions give off heat. So in the refinery, that's fluidized cat crackers, FCC. It's hydrocracking. In our lab that we're looking at is fermentation. Typically, this happens when we have molecules and we're breaking them apart. Okay? Generally, we give off heat. Endothermic reaction is catalytic reforming, hydrogen generation at the oil refinery. Or an example you have at your house is cooking, right? So if you're cooking, if you're frying eggs on a skillet, you take that raw egg and turn it into a cooked egg. What's it take to get there? It takes heat, right? Endothermic means it takes in heat. It takes heat to make the reaction happen. Exothermic, it gives off heat. Okay. One of the most common, easiest exothermic reactions to think about is, the combustion of gas, right? So when that's a chemical reaction that happens and it gives off heat. Another type of reaction we have is a neutralization. Acids and bases, hydrogen ions and hydroxide ions, adding in them and taking them away. To neutralize it, we end up with, two H's and an O, so H2O, so we end up with neutral, which is water. And they reduce the acidity or alkalinity of a solution. Okay, so they neutralize each other. Combustion, the book kind of lists it as zone. It is an exothermic reaction. It is a highly exothermic reaction, and it's going to have fuel, oxygen, and a heat source to be able to happen. The next part of this chapter goes into material balancing, which we get into in chemistry class a lot. But we want to talk about why we have to do that and what that means. So if we have fermentation, this is a molecular formula for sugar, C6H12O6. Okay, that's going to turn into alcohol and CO2 when we look at our hands on the lab. This is a molecular formula for alcohol, and this is a molecular formula for carbon dioxide, okay, CO2. Now notice this has 6 carbon atoms here on this side. In order to balance this, we have to have 6 carbon atoms right here on this side. Okay, and so if we don't add these 2's in front of it, then what happens is we don't end up with 6. So here we have, 1, 2, and then we multiply it by 2, so that's 4, and then we have 2 over here, so that's 6. Okay, so we have 6 carbon atoms on the left, we have 6 carbon atoms on the right. Okay, that has to happen, otherwise we wouldn't have, chemically it's impossible. Chemically, it's impossible if we don't end up with the same amount of material on the left as we do on the right. Okay, those atoms aren't being created or destroyed, so they're just moving around. They're just changing who they're connected to. We have 12 hydrogen atoms here, H12, and here we have 10 because we have 5 times 2 is 10. Plus we have 2 more over here because there's no subscript right here, so that means there's just 1. So we have 10. Part of this, and then we have 1 bonded to this OH right here. Okay, so that's 12 hydrogen. 6 oxygen over here. Here we have 2, and here we have 2 times 2, which is 4 more, so we have 6 total. Okay, and what does this matter? Because this is going to happen in a reactor. Okay, why does it matter? Well, if we go to something simple, which is methane combustion, methane is natural gas. That's the CH4 right here. We need oxygen in order for that to happen. Okay, so if we have oxygen here, that's going to turn into carbon dioxide and water. And it's also going to give off a bunch of heat, right? That's what we do. one methane molecule combusts with 2 oxygen, creating carbon dioxide and then 2 water molecules. Now, if we have incomplete combustion, so here we have 2 oxygen for every 1 methane, okay? If we don't see, the number in front of here, we assume it's a 1, right? So if we have 2 oxygen for every 1 of methane, which means we have plenty of oxygen, we have a complete combustion. Now, what happens if we don't have enough oxygen going into our furnace? And let's say instead of having it 2-to-1 ratio, we only have it 3-to-2. Okay, so if we don't allow enough air going into our furnace, then we end up with a ratio of 3-to-2 instead of 2-to-1. Well, then what happens is we end up making carbon monoxide and water. Okay, carbon monoxide is a carcinogen, right? It's harmful to breathe. We don't like it. We don't want it. It's a poison to us. Carbon dioxide is clean, can be released out in the atmosphere, no problem. Carbon monoxide cannot. And so if we don't have enough, this is what you can control over here, is these numbers over here, this 2 and this 3 as an operator, okay? You can open up the dampers of a furnace to allow enough oxygen to get in there to get to that 2-to-1 ratio instead of being a 3-to-2 ratio. So if we have this, if we don't allow enough oxygen, then that changes our chemical reaction, and we end up with carbon monoxide. Notice there's no 2 here, it's just 1 carbon monoxide, which is a different molecule than what this is up here. I have another separate PowerPoint where we go through a lot of these in more detail, but this is why we have a lot of focus on reactors, is because we see reactors all over the chemical industry, we see reactors all over the crude oil industry. And why we see them is because this part of a barrel of oil, so this is a barrel of oil that we get from the ground, okay? So just drill down and get it from oil sands in Canada. This part right here that I'm kind of drawing a line by is our money maker part. It's our useful part, okay? This is what we can really get money off of, right? Gasoline, materials, okay? And then this down here, we don't make any money off of. This is kerosene. Don't make any money off of this. We make money a little bit off of this too. Actually, we make a lot of money off this blue part too here. Okay, so here we have just a little bit of the gasoline components. Here we have just a little bit of the diesel fuel components. Gasoline, jet fuel, and diesel fuel are what we really make money off of for a oil refinery. Okay, so we have a little bit up at the top, a little bit at the bottom when we drill, and if we just separated it out and just used it like this, we would have a little bit here and a little bit here to make money off of. Well, if you notice how much we have the orange and the red and the blue down here, it's way more of that barrel of oil. And that's because we went through all these reactors. Okay, so same barrel of oil, we changed the molecules, we did a chemical reaction, and now we're using most of the barrel of oil. Here we're only using about 50% of it. Here we're using over 75% of it, and we're selling it for our money-making products. Okay, kerosene gets smaller. We don't sell much kerosene. All this residual, this ends up being, asphalt, fuel oil, heavy fuel oil, which some people use in their still, but not much anymore. Like ships and things used to, but now they basically run on diesel for the most part. And so all this stuff is just kind of residue that we don't really make any money off of. Okay, so we want to try to limit that amount as possible. We want to increase the amount of jet fuel, diesel fuel, and gasoline. Those are the big ones that oil refineries make lots of money off of. And so in order to do that, this is what the crude oil refining process looks like. This is a brief overview of pretty much what's going on down in the Wood River refinery. Bring in crude oil right here. We go through a bunch of different things. We'll talk about desalting in chapter 16. We go through distillation next in chapter 15. And so far we haven't done any reactions. These are where we're doing some reactions here. Cat cracking, hydrocracking, hydrodesulfurization, okay, cat reforming, Okay, more hydrodesulfurization, a lot of sulfur in here. Alky, that's going to be a reaction. Coking, that's a reactor that we have there. Okay, all these parts in here that I circled are going to be part of chapter 14. Okay, these are all the different reactions that we have going on. Okay, and then when we have those, then we get a lot of gasoline, jet fuel, and diesel fuel because we have these reactors. Okay, that's kind of why we do reactors, what goes on. The next part of this is, getting into the 5 main types of reactors. Make sure you know those. A vessel in which a controlled reaction takes place. Before we get into those, the 2 main types of operation methods, batch and continuous. Batch, think of that as like your process of cooking supper. You put everything in a pot, you cook it, and then it's finished, and it's done. And then what do? You clean it back out, and you start the whole process over again. Okay, so we clean the vessel out, we charge it with material, we let it react, and then we dump it all out. Continuous, we start it up and we run it. And so we continuously feed reactants in here, continuously stir it around, and continuously have products going out this direction here. Okay, so we just initially charge it and fill it up once. Now the advantage to continuous, main advantage to continuous is it doesn't take nearly as much time because we just fill it up once. Right here, when we're using a batch, we're not making any money while we're cleaning it. We're not making any money while we're initially charging it. We're not making any money while we're letting it sit in there and react. We're only making money when we're pumping the products out, okay, and only in the finishing. Okay, here we're making money for the whole time that we're doing operations. And this continuous reactor might run for 6 months, might run for a year, might run for a couple years without ever shutting down. And so they're constantly making money. This is the style that we'll look at in the lab. Okay, the reason we use this in the lab in the ethanol industry is this component right here, this cleaning. Okay, since ethanol in reaction is a bioreaction, that means it's a living reaction. It is subject to contaminants. And so if we get bacteria in there, if we get any type of harmful bacteria that's going to kill off our yeast, which is going to kill off our catalyst, the reaction won't work properly. And so we have to dump the material out, use it up, and then clean the vessel out. Okay, so that's a main advantage to batch. We always like to use continuous in industry if we can. If we can't keep it clean enough, using it continuously, then we have to go in and do a batch style reaction. Stirred reactors, this is the reactor we're going to look at in the lab. Okay, just think of it as a tank with an agitator. Agitator is this part right here that spins around, keeps everything nice and mixed up. All these are shown as different ways that we can add and take away heat, which we'll see what those look like in the actual hands-on labs. This is the reactor right here that we're going to look at. One of them here is the same thing, just bigger. This picture's taken down at Center Ethanol. These are 500,000 gallon reactors. Okay, so they get filled up with material, and then they react and convert that sugars into alcohol. Okay, fixed bed, which is a converter. We have feed material come in here. We have a fixed bed of our catalysts. Okay, and so we'll show you in the hands-on lab what this looks like depending on what the reactor is. So it's fixed in there. So there's a screen up here and a screen down here that doesn't let the catalyst out. Okay, it's a dry material, solid material. Feed comes down through here, comes into contact with the catalyst all through this bed, and it comes out as a final product down here. Okay, hydrodesulfurization, hydrocracking, and reforming use these, and that's what these look like in the industry. Here we have the bed of catalyst. High pressure. This is one of those that the higher the pressure, the quicker, the better the reaction is going to be, because we got to force that liquid into these fixed beds. Fluidized bed means we have this solid is going to be our catalyst, and instead of having it fixed into one place like we do here, this is constantly moving around. It's in a fluidized bed, so we have solids all moving around here. And notice there's no agitator in here because as those solids are moving around, they're agitating the material up. And so they're coming into contact with our gases. Okay, so they're coming into contact with our material that we're trying to react with. Okay, so they're having the raw materials come in and then go out as a final product. I'm going to talk about these in another lecture in a little bit more detail and show you a little bit more about what they're looking like. Okay, but notice that the solids, the catalysts, are constantly being fed in and constantly going out. They're not fixed. Okay, they're floating around and moving around. And then we'll show you what it looks like after those contaminated solids go out. Tubular reactor, think of this as a shell and tube heat exchanger. What we have inside here is we have the reaction taking place. We use these for chemical synthesis. We use these where temperature is very, very precise because we have a lot more surface area that we can control the temperature. Here, if we go back to these style, we can control the temperature, but we have a big tank here, upwards of 500,000 gallons or so. And so the temperature not going to be even all throughout. It's going to have some hot spots and some cold spots. We want to minimize that, but it's inevitable. Sometimes the top of the tank might be a little bit hotter than what's on the bottom of the tank. Well, if that's very precise and needs to be very controlled, we put in the shell and tube heat exchanger and have the reaction happen right in there. That way we can really maintain the temperature of that correctly. Furnace is a style of reactor. So we learned about furnaces back in equipment class. If inside these tubes the material is breaking down and changing chemical composition like it does in a coker in the oil refinery, then that means it's a reaction furnace. Okay, and so this happens in this furnace. Not all furnaces are reactors. Some furnaces just heat up the material, but this is actually heating it up to the point where it's having a chemical reaction happen. Okay. Problems with reactors. Well, the main one that we have is a runaway or an out of control reaction. And if we remember back to the beginning, one of the first slides, if we increase the heat, we increase the reaction rate. Okay, so it's going to happen quicker the hotter it gets. Also remember that one of the types of reactions that we have is exothermic. Exothermic means it gives off heat. So if we have a reaction that gives off heat and it also goes faster as it heats up, that can be an out of control reaction. If we can't pull the heat out, we heat it up, it reacts, it's exothermic, which means it creates heat, which means it's going to get hotter, which means it's going to happen faster, which means it's going to create more heat, which means it's going to happen faster, which means it's going to create more heat. If you see how that is, that's a runaway, out of control reaction. So we have to be able to pull the heat out using some kind of a heat exchanger in order to control that. This is one of the reasons why we might add inhibitors. If you remember back at close to the beginning, we talked about inhibitors. Here, they hinder the reaction. Okay, sometimes we will add inhibitors into a reactor because we want to slow it down so it doesn't become a runaway reaction. Other things, contaminants. Sometimes we add inhibitors to keep it from being an out of control reaction. Sometimes we have inhibitors and contaminants just come in with our feedstock, with our material. That happens to be one main one in the oil refining industry is salt. Okay, so we have the very first step is desalting. Okay, if we let that salt get through there, that will be an inhibitor to our process. And then pluggage. So if we plug materials, if we end up with materials being plugged, cooling lines being plugged, things like that, that would affect our reactor. Here we have a picture of an explosion at a reactor. This has happened because of an out of control reaction. We got a YouTube video we'll show you in another class about that. Last slide here is the reactor systems. And this is what we have going on, and this is what we'll look at in the lab. As well. It's going to look very similar to this. Here we have our two reactants, one right here and one right here. That's what's going to be reacting to each other. This is a continuous stirred tank reactor. And so it's stirred because it has an agitator. It's exothermic. We know that it's exothermic because we're putting cooling water in here. Okay, so we're adding cooling water not into the reactor, but into a jacket around the reactor. We'll show you what that looks like in the lab. Controlling the level, we fill this up initially once, reaches a level. After it reaches that level of 75%, this control valve will open, maintaining that 75% control. Okay, so we're constantly adding material in, constantly mixing it up, constantly letting it go out. One of the safety aspects we have of this is a cooling water that keeps the temperature down where we need it to be so it doesn't get a runaway reaction. Also, we have this vent, okay, this vent that goes out to a flare. So if the pressure gets too high, above 85 psi, this valve opens up, allowing the gases to go out to the flare, and they can be safely burned off there. Okay. We get the feed in controlled by the reaction, so we make sure we're constantly have an online analyzer, making sure we have the right concentration of butane coming in here, coming out here. And so if it needs to have less butane, then we increase the amount of feed that going on this line. So FIC 211 will do that. Okay. Speed control on our agitator will run. If we need it to react quicker, we can speed this up. If we want it to react slower, so say our temperature is getting too hot, our pressure is getting too high, we're having too much of a reaction take place, we can slow down our agitator here. Or if our temperature is not high enough, if our pressure is not high enough, we can turn this on to speed up the reaction. Okay, let me know if you have any questions. We will see you in the lab.